Assalamualaikum. Good evening. Okay, today we are going to continue with other topics. We will learn how to describe wave. First, you have to know the terms wavefronts, amplitude, wavelength, period, frequency, and speed of wave. Before we start, let us look at this video. So as you can see, water wave have crest and throw. A crest is the highest position of the wave, while a throw is the lowest position. Imagine that the screen is the surface of still water. Okay, what do you think may happen if you dip a finger into the still water? Yes, you will see a dark and bright line. So the dark and the bright lines are called wavefront. So what is wavefronts? Wavefront is the line joining all the points of the same phase. The wavefront depend on the point of the source. The first one, a point source emits circular water wave, and a long straight source will emit a plane water fronts. So we repeat again, what is meant by wavefront? So wavefront is lines joining all points of the same phase. Two points have same phase if both points have same displacement and move in the same direction. For example, in this circular wave, so we dip a spear dipper, so we produce a circular wave. So look at point A, B, C, D. Point A, B, C, D are all in the same phase because all of them are at the crest. And point E, F, G, H are all the points on the throw. So A, B, C, D will vibrate upward, while E, F, C, H will vibrate downward. So the next one, we have a vibrator, a plane vibrator. So when we vibrate, it will produce a wavefront, and when we look at from the top, we look it is a straight line. So we call it a plane wave. So point A, B, C, D are all the points on the crest, and this will vibrate upwards with the same displacement, while point E, F, G, and H all on the same phase because they are all on the throw. So this point will vibrate downward. So we said that A, B, C, D are the points on the same phase. So we line up so to produce a line, and it looks something like this. Okay. Next, look at the direction of propagation of the wave and the wavefront. what can you say about the direction of propagation of wave and the wavefronts? So the direction of propagation of wave is perpendicular to the wavefronts. Now look at the circular wave. So what can you say about the direction of propagation of the circular wave? The direction of propagation of the circular wave is radially outward, which is perpendicular to the wavefronts. So this is another video to show a plane wave produced by a ripple tank. So if we see on the bottom on the screen, this is the straight line or the plane wave. We have the bright and the dark color alternately. Okay. So look at activity 4, observing wavefront. Okay, show the direction of propagation of wave by using arrow. So this is the plane wave, and here is the circular wave. So the wavefronts and the direction of wave propagation are perpendicular to each other. So this is radially outward, and this is the wavefront, which are perpendicular to each other. So we observe that the wavefronts are perpendicular to the direction of propagation of the wave. Okay, we can look at the ripple tank. So the wavefronts is a plane, and the wave is moving from top to bottom, and they are perpendicular to each other. So the wavefront is perpendicular to the direction of propagation of the wave. Now we proceed to describe the wave. So activity 4 is to study amplitude, period, frequency of wave and wavelength. So first we look at what is the meaning of complete vibration or oscillation. So the movement from one extreme position to the other and back to the same position. So the movement of to and fro. Okay. We have two examples. This is the pendulum bob, the pendulum system. Okay, so we start with P. So from P to Q to R, and go back to Q, back to the same position P. So this will be the one complete oscillation. And for the spring, we start from 0 to B, move to back to 0, move upward to A, and back to 0. So this will be one complete vibration. Next is the amplitude. So amplitude is defined as the maximum displacement from the equilibrium position, and SI unit is meter. So this is the equilibrium position, the position where before the wave start. Okay, so here is the maximum displacement from here to the maximum to the crest, and here from the equilibrium position to the throw. Okay, next. Okay, so the maximum amplitude is the maximum displacement of the object from its equilibrium position. So we have the pendulum here. So this is point O to A, and here from O to A. And here is from vibration of the spring from 0 to B downward, back to O, and go up to A. So the distance OB is amplitude, OAU is also amplitude.
Watch the pendulum swinging back and forth.
So this is the pendulum.
Watch the pendulum swinging back and forth. When the pendulum swings from A to B and back to A, the pendulum is said to have done one complete oscillation.
So we have first the next definition, period, symbol T, time taken for one complete oscillation. SI unit is second. Time taken from O to B back to O. Okay. So count how many complete oscillation are there in 5 seconds. So we have 10 complete oscillation in 5 seconds. Okay. So the processing ball made 10 complete oscillation in 5 seconds. So first question. Okay. Calculate how many oscillations the processing ball make in 1 second. So how are we going to do that? So we have 10 divided by 5. So we get 2 oscillation in 1 second. So we have the next term, frequency, the number of complete oscillation made in 1 second. SI unit is hertz or per second or S minus 1. Okay, next. So, period is the time taken for one complete oscillation, while frequency is the number of complete oscillation per second. Again, we look at this calculation. So, the time taken for determine the time taken to make 10 complete oscillation. So we have t equals to 5 seconds. The period t equals to 5 second divided by 10, you get 0.5 second. The frequency is number of oscillation per second. So we have 10 oscillation divided by 5 second, and we get 2 second minus 1 equals to 2 hertz. So period is the time required to complete one oscillation. The formula is time taken divided by number of complete oscillation. 5 seconds divided by 10, you get 0.5 second. Frequency is the number of complete oscillation per second. So T equals to number of complete oscillation over time taken. So number of 10 complete oscillation divided by 5 seconds, we get 2 hertz. Therefore, compare the two formula. How is period related to frequency? So we have F equals to 1 over T. F equals to frequency equals to 1 over period. So the equation is F equals to 1 over T, and the SI unit for hertz is S minus 1 equals to hertz. Now we move on to the meaning of wavelength. So wavelength is the distance between two successive crests or throw. What is meant by successive? So we have here one crest, another one is one crest. So they must be 1 and 2. That is what is successive. This is called lambda or wavelength, or from one throw to another throw. So this is also lambda. Again, remember the slinky spring for longitudinal wave. We have a compression, refraction, another compression. So one compression to another compression is what we call wavelength. And the distance between the one refraction to another refraction is also lambda. So let us mark and label wavelength. So one crest to another crest. Here is lambda. Or throw to another throw, or the distance between one compression to another compression, lambda, or from one refraction to another, refraction. So this is also called wavelength. Lastly, we have a speed of wave. So we have here is a ship searching for MH370 at Indian Ocean. Okay. So look at the wave. This is the crest, and the boat or the ship is moving forward. So we have the speed, symbol V equals to distance traveled per unit time. SI unit is meter per second, ms minus 1. So the speed of wave is the distance traveled by a wave per unit time. So the speed of wave tells how quickly the energy which is carried by the wave is being transferred. Okay, let's do some exercise. Exercise 1. Diagram 1 shows a wave traveling in the sea starting from point A. So we have A to G. The first question, indicate the interval which represent one wavelength. So we have A to E, F starting, and the end. So A to E, the distance between A to E. Another one is crest to another crest, distance between B and F. And also from C to G. So C and G. Right. State pairs of points which are at the same phase. So phase A, E. So this will be upward, is also upward. BF also upward, F also upward. C going down, downward. D down, and also G going down. State the direction of propagation of the water wave. So it will move from left to right, or A to G. Question number 2. Based on diagram 2, calculate the wavelength. So the distance from here, the beginning to the final position, we have 5 lambda, 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda. So what you do is 20 divided by 5 and we get 4 centimeter. Last question. Diagram 3 shows a steel ruler which is clamped to a table and is oscillating following the path A, B, C, B, A. So from A, B, C, B, A. First, the time taken to oscillate 10 complete oscillation is 8 seconds and distance AC is 12 cm. So determine the amplitude. Again, amplitude is from equilibrium position B to the maximum displacement A. So the distance is 12 divided by 2 equals to 6. How about the period? So the period is the time taken for one oscillation. So what we have is 8 seconds divided by 10 and we get 0.8 second. It means that from A to B to C, back to B, back to A, it takes 0.8 second. How about the frequency? Frequency is the time taken for the complete oscillation for 1 second. So what we do is formula 1 over T, 1 divided by 0.8 and we get 1.25 Hz. Okay, that's it for today. See you next time. Goodbye.